Log on, tune in, find out. Another good idea from Cambridge.
It gives me great pleasure to welcome Lacrimioara Iancu from Aberdeen, who will tell us about the Combinatorics of Kazhdan-Lusztig cells.
Thank you. Thanks to the organizer of the seminar for giving me the opportunity to talk here, and more generally, thanks to the organizers of the program for giving me this really good opportunity to be in Cambridge for the first time in my life. And so today, some things about combinatorics of Kazhdan-Lusztig cells. Actually, the title should be much longer, possibly something like in the framework of unequal parameters and with a special emphasis on type B. So what I want to talk about is some work in progress. It has been in progress for quite a number of years, I have to say, on the determination of Kazhdan-Lusztig cells in type B for all choices of parameters. So I will start by explaining a bit I hope I will be quite fast there at the beginning, the ingredients which are involved in the Kazhdan-Lusztig theory. So some things about the Hecke algebras, then Kazhdan-Lusztig basis, then cells, and then we see the problems that arise. This talk is clearly a continuation of the the lectures given by Cédric Bonafé in the first 2 weeks of this program. So let me start by saying how we will look at Coxeter groups. We'll take S to be a finite set and a matrix consisting of integers and possibly infinite. These numbers, the entries of a matrix, will represent the powers, the order of the product ST in the group W. So the corresponding Coxeter group is defined by a presentation of generators S and relations given by what we read in that matrix. That is, MST is the order of the product ST in the group W. In particular, every S is of order 2, so we are talking about reflections there. Usual examples, the dihedral of order 2m is a Coxeter group with such a Coxeter presentation, and the symmetric group on n letters is also a Coxeter group with Coxeter generators S1 up to Sn minus 1, the transpositions I plus 1, Si is I plus 1. So in every such Coxeter group, we can introduce a length function. That is the obvious notion. So the length of a minimal expression of an element W in terms of Coxeter generators. And so we are going to define the Hecke algebra associated to a Coxeter group and a weight function. So far we have seen what a Coxeter group is. Now what will be a weight function? So the weight function will be a function which will simply pick some parameters for the Hecke algebra. So how you do this is to take these parameters out of some abelian group. So let gamma be an abelian group. And we call weight function any function which has a behavior somehow similar to the length function. What is this behavior similar? Well, it behaves like homomorphism whenever there is no cancellation between W1 and W2 when you multiply them. So if you look at this definition, you can see that the length function itself is a possible choice as a weight function. And that is what is called the equal parameter case. Also, because of what we have said before about reduced expressions and what is known about reduced expressions in Coxeter groups, actually the weight function, the values of the weight function on W are perfectly determined by the values on the generators. Of course, if that is a reduced expression, this I really like, so I have to use it. If that's a reduced expression for W, phi of W will simply be phi of S1, phi of S2, and so on, phi of SP. Not only that, but actually, so it's enough to know the values of phi on S, and actually even less than that, it's enough to know the values of phi on the conjugacy classes of generators. So if the order of the product ST is odd, then actually S and T are conjugate in the group. And what we ask is phi of S to be equal to phi of T. So basically all we need to know is values of phi on conjugacy classes of parameters, which means that if we stick to the case of finite reducible Coxeter groups, unequal parameters can only occur when we deal with dihedral groups, so I2 of M with M even, Bn and F4. Now I2 of M and F4, well, I2 of M dihedral is a case which is dealt with quite easily, so, and F4 is one single group which is dealt with in, I will say later where. So this is why I'm going to concentrate on type B, on Bn. So we have the Coxeter group, we have the weight function, so we can talk about the generic Ivahori-Hecke algebra associated to this data. So it's an algebra over A, whereby A would denote the group algebra of gamma. So gamma is the group where we take the parameters from. The parameters of the algebra of phi of S are phi of S, so the weights of the Coxeter generators. And it's defined as follows. It is an associative algebra. It is free over A with a basis indexed by the elements of the group, of the Coxeter group. And the multiplication is given by those two relations there. Namely, T of W is T of S1, T of S2, T of SP. If W equals S1, S2, SP is a reduced expression. Please note that this, actually, I mean, one has to prove this first. It can be proved that this definition does not depend on the choice of the reduced expression for W. And then, what happens when there is some cancellation? So Ts squared, and it's there that the parameters occur. This is how you square the Ts. It's phi of S minus phi of S inverse times Ts plus T1. In particular, this also shows that Ts is invertible, and then all the TWs actually are invertible. So the algebra has a basis T formed by these elements TW. This is how they multiply, and please note that they are all invertible. Now the advantage of having such a generic object is that then you can think of specializations. So if small k is any field and theta is a ring homomorphism, then of course you can construct H sub k by extending the scalars. And well, it has similar properties. It's an associative algebra with a basis labeled by the elements of the group, and multiplication just obtained by the above, where phi of S is replaced by theta phi of S, which would denote by QS. Now, of course, this brings us immediately into a huge universe, because you can think of many, many specializations. So this would be one important aim, to understand the irreducible representations of H sub k for various such specializations. Why is this an aim? Well, first of all, we could say as such, because the object is there, but not only that. Actually, it quite well known that, well, maybe I should say something more, that the representation theory of this Hecke algebra here, H sub k, is in a nice bijection, a nice correspondence, well, the irreducibles, with some irreducibles of some groups coming from, well, groups of Lie type. So very quickly I will say what I mean by that. So if we have a finite group of Lie type over Fq, where Q is some prime power, then such a group has a Bn pair, where B is a Borel subgroup, and the Weil group. And if you take K as before, some field, but this time let's take it an algebraically closed field of characteristic 0 or not dividing Q, then if you consider, well, not the set of all irreducible representations of G, but only those which have this property, that there is some non-zero vector fixed by B, then that set, this is a classical result, well, classical some part and some other comes from Dipper in the 90s, that there is a natural bijection between those irreducible representations of G and the irreducible representations of HK, of the specialized Hecke algebra. Where, so what is the specialization? Well, in each case, in each particular case, one can explain exactly what the specialization is. But in any case, it looks as follows. Theta sends the parameters of the Hecke algebra, the phi s, to such elements of small k, q to some, q is this q here, q to some power times the identity, where that power is a positive number. So, for example, if we think simply of GLN, then, okay, its Weil group is of type A, so parameters are all equal. Phi of S is the same for each generator there. So in our specialization, the specialization will be simply Q to the power 1. So the CS there will be simply 1 here. If you think of finite unital groups, then the Weil group is of type B, Bm, where m and n are in this relation. M is n minus 1 over 2 if n is odd, or n over 2 if n is even. And in those cases, the choices of parameters are either 3, 2, 2, 2, 2, or in the case where n is even, 1, 2, 2, 2, 2. Yeah? So these were just examples. So for every single, well, all cases, you can figure out, there's some procedure where you can figure out these things. But of course, this doesn't seem to justify the interest for having a look at a wider choice of parameters. So for the time being, for instance, in type B, I'm saying it's interesting to look at equal parameters or at those two things, 3, 2, 2, 2, or 1, 2, 2, 2. Well, actually, more general types of parameters can occur. So here, all this story comes from essentially the Hecke algebra appears as endomorphism algebra of here you have the permutation representation, and then you take the things there, and this would be this HK. Now, and well, this you can look at this as being the induced of the trivial from B to G. Now, if you look at something which is some variation of this, so instead of taking induction, you take Harish-Chandra induction, and instead of going from the Borel to G, you start from parabolic subgroups. Actually, you do Harish-Chandra induction from Levy subgroups, and you do this not only on the trivial representation, but on cuspidal representations. what you do, you have many other Hecke algebras occurring, and in particular, more general types of parameters occurring there. Okay. So this would be some motivation for studying at all the representation theory of those Hecke algebras. So now let's return to that Hecke algebra. For the time being, we stick to being over the ring, well, over the group algebra A. And the Kazhdan-Lusztig theory of cells gives exactly this, a general method for constructing representations, not necessarily irreducible. What is the advantage there is that in many cases the cell representations are irreducible, or if they are not irreducible, well, they give a decomposition of the regular representation, so you can be certain that you will find all the irreducibles there somewhere. And they are not very big in some sense. So there's good, and the theory gives quite a good idea of what irreducibles occur in cell representations in any case. So what we still need to see is the Kazhdan-Lusztig basis. So far we have seen the Coxeter group, the weight function, the Hecke algebra, and specializations. If we want to talk about Kazhdan-Lusztig theory, we need the Kazhdan-Lusztig basis, but that does not come like that. It comes at a further price. We still need two more things. What we need is a total order on gamma. Remember, gamma was the abelian group where the parameters live. We want it to be compatible with the group operation, so actually what we need to be able to compare the parameters of the Hecke algebra. Look at them and say one is bigger than the other. Something like this. And not only those, but to be able to compare those and any power of them. So for this purpose, a total ordering on gamma, which is compatible with a group operation, denote by gamma plus the elements which are greater than the identity, by gamma minus the inverses of those, and gamma appears as well, this joint union of those three sets there. And there is actually no loss of generality if we suppose that 5s is always in gamma plus, so all parameters are positive in some sense. And the last ingredient needed for introducing the Kazhdan-Lusztig basis is the bar involution. So we start with a map defined on A, which sends every element of, so A was the group algebra of gamma, it sends every element of gamma to its inverse, and it extended to an involution of H in the following way. So take an arbitrary element of H, it's a linear combination of TWs. So TWs use the elements of the standard basis of H. The bar map sends this to AW bar, which comes from here. The AWs are just coefficients. And it sends the TW into the inverse of T sub W inverse. And now this is what Kazhdan-Lusztig did in 1979 for the equal parameter case. And for the more general case, unequal parameter case, Lusztig did this in 1983. One has to say that it's essentially the same proof, so the important result is the one in 79. They showed that one can find a basis of H. So for each W, we define CW by asking that those CWs are invariant under the bar convolution, and by asking that when expressed in the standard basis, so CW is TW, so TW occurs with coefficient 1, and it has something like this. So in other terms, the transition matrix is unitriangular. This is what it says here. Here, this inferior is the Breuer order on W. And those coefficients which occur there are coefficients in A minus. So they just contain, there's Z-linear combinations of elements in gamma minus. And actually those coefficients are what we now know as the famous Kazhdan-Lusztig polynomials. So the proof is quite elementary, and as I said, the essential proof is given for the case of equal parameters. It proceeds by induction on the length of W. So you start with C1, which will be equal to T1, then with CS for all the simple reflections, we get CS equal to TS plus 5S inverse times T1, and so on. Those coefficients, as I said, are the Kazhdan-Lusztig polynomials. They can be computed by using recursion, so there is a recursive formula coming from this actually, but there is no closed formula for them. And there is no, well, there are other specialists who know really many things on them. So for instance, at least for the equal parameter case, it is absolutely clear that any polynomial in Q, in the equal parameter case, let me say any polynomial in Q with positive coefficients can occur as Kazhdan-Lusztig polynomial for some group in some algebra. So you cannot. So it's not there. It's not like this that you can find some closed formula. And let me denote the structure constants by h, x, y, z. So in this place is the multiplication. We'll have some structure constants denoted by h, x, y, z. So now we are ready to talk about cells. So we are going to define some relations on W. First, a preorder. What I mean by generated is, I mean it's transitive closure. So the elementary step is, we say that x is left inferior to y if you can find some S in S such that the product CS Cy contains somewhere a Cx. For CS Cy you can express it as a linear combination of Kazhdan-Lusztig elements of the basis, and Cx appears there with some non-zero coefficient. Or with the notation of my structure constants there, this means HSYX is non-zero for some S. Now whenever you have a preorder, you can define an equivalence order by just declaring that x is equivalent to y if x is less than y and y is less than x. So left equivalence if this holds. And then the equivalence classes are called left cells. Now similarly, we can talk about right preorder and right equivalence and right cells by just using the right multiplication. So x is right inferior to y if Cx appears with non-zero coefficient in Cycs for some s. Also, there is something which can be proved, which is sound as follows, that x is right inferior to y if and only if x inverse is left inferior to y inverse, which means that is we can stick to left cells from now on and to left preorder, because once you know one, you know the other. There's also a third preorder, the left-right, which is generated by the union of left, the left inferior and right inferior, so left preorder and right preorder, and which gives rise to a left-right equivalence and to two-sided cells. So it's quite an effort that we do there. We start from a Coxeter group, take weight function, produce a Hecke algebra, choose there, and ordering all this in order to define some relations on W, back in W just. But this is quite a strong setup, so it will give rise to some interesting things, namely to some representations of H, actually. Before I explain that, let me just point out again that any choice of ordering on gamma gives rise to a corresponding Kazhdan-Lusztig basis. So you have the algebra, but whenever you change the ordering between the parameters, the Kazhdan-Lusztig basis will change, and as a consequence, the cells, the partition of W into cells changes. So now, I was saying we can see the cell modules or cell representations. How are they defined? So once we do get hold of such a left cell, we can define two A modules. Here just the A span of the CYs. So you have the cell, then you look at all elements which are left inferior to some element of the cell, which means to any element of the cell. So either such a Y is either in the cell itself or below in this relation, left inferior. And take the A span of all those. And similarly, take the A span of all those, but exclude those which are in the cell. So you want those which are, if you like, strictly less inferior, left inferior, sorry. Well, it turns out that because of the way this relation is defined, they are both left ideals of H. And because of this quotient here is an H module. And it's an H module which is actually free over A. It has a basis, well, it's quite clear, it has a basis indexed by the elements of the cell. So by By, for instance, I understand simply the Cy there, plus Ic hat. And, well, the action of H is simply given by the same structure constants as before. Of course, you only look at those which, so it kills everything which is not in the cell. So Cw acts on Bi, well, on the cell. So times By, sorry, is such a linear combination where, of course, the Bx here are only those in the cell. And under any specialization, we obtain corresponding cell modules. So these relations, and similarly, we can define right modules, right H modules, and bi modules, H bi modules. So these partitions of W into cells provide representations of H and also of those specializations. So let me take now an example. So of course now the problems are as follows. Given a certain group and a choice of parameters, find the cells, find the corresponding representations, decide at least under some specializations if they are reducible or not, or when they are reducible, whatever, something like that. So in type A, well, here are the generators, equal parameter case because they're all conjugate, so phi is constant. Essentially, there's one choice, whatever you declare the parameter to be, it's one and the same for all of them. So call gamma this. I mean, it has to be a billion, so it looks. You don't care. It can be bigger, but this is all you are interested in anyway. So call V the parameter. This is what I mean here. So the phi of S, I may have forgotten this. Phi of S is just V, and regard V as an indeterminate. So A is just the ring of Laurent polynomials. V. Gamma is the set of all powers of V. Gamma plus the obvious choice, just the positive powers. What Kazhdan-Lusztig showed in that 1979 paper was that left cells can be described in terms of the Robinson-Shenstedt correspondence. I will explain briefly. Give us a short example immediately. Let me finish the story here. Also, if you take exactly this specialization, if you like, where capital K is really the field of fractions of A, then the specialized cell modules, cell representations are all irreducible, and all the irreducibles of HK arise in this way. And of course, on the other hand, Dipper and James have introduced the Specht modules in '86. This is a collection of modules of H which have the property that when you go into HK, this collection is really the collection of all irreducibles of HK. So of course, then you have a natural question: is there a nice bijection, nice correspondence between the Specht modules of Dipper and James and the left cell representations, which are all irreducible as well if you look at HK? So the answer is positive. It was given by McDonald-Palikaris in 2005. They really gave a canonical H isomorphism between the Specht modules and the cell modules. I'll come immediately to these Specht modules, why they are nice, why they are good, but I'd like to just briefly give an example on. So I'm in type A5. Sorry. I take here a permutation described like this. Now what does this Robinson-Shenstedt correspondence do, and what is the result of Kazhdan and Lusztig really? So the Robinson-Shenstedt correspondence is a procedure which associates to every element of the symmetric group a pair of Young tableaus. And how is this done? Well, there is an insertion procedure which goes something like this. You have to produce a pair of tableaus. So the first tableau is obtained by insertion. The second tableau just keeps track of what you did on the other side. So at the beginning, you insert your 2 there into the empty tableau. And so you have a little box like this. This is the first box that you put there. Then the second box is a 5. The insertion algorithm says you just try to put it. It has to be a standard tableau, so everything is increasing on rows and columns. So you try to put it on the first row if possible. Well, here it is possible, in the sense that if it's bigger than the one before. So here, okay. Then comes the 3. You cannot put it here because it's not bigger than 5. So you put it there where it should be, in the sense that you have to find on that first row the place where you can the first place where you can find an element which is smaller than the one you are trying to insert. So here you will want to insert the 3. So you insert it there, and what happens to the one which was there? It's bumped. It's called a bumping procedure. It's bumped on the next row. If it finds a good place, it stays there. Otherwise, I mean, it will have to stay in the next row, but either it stays like this, as it will here, or it will bump somebody else further. So here, keep track of what we are doing. From here to here, we have added this third box. And we continue so on. So now we have to insert the 1. It has to go really in front there, so it has to bump the 2 down there. The 2 has to go down, but then it bumps the 5. So what we have done here, there we are. Then we have to add, we are here. The 6, well, that goes happily there. And finally, we have to add the 4, which has to go there and bumps the 6 on the next row. So it's 1, 3, 4, 2, 6, 5. And this is really the last box that we have added. Yeah. So give them a name, call this first one P, and the other one Q, whatever. So once more, the first tableau is obtained by this insertion procedure, and the second one by keeping track. Now, the Robinson-Shinstead correspondence is a result from the 30s, something like this, which says the following thing. It says that there's a one-to-one correspondence between the symmetric group on n letters and the set of all pairs, all pairs of standard tableaus of same shape. They have the same shape. Size n, and filling with the numbers 1, 2, up to n. So in other terms, if you're given that pair, you can recover the element, of course. And not only that, actually that's a very nice correspondence. It has the following property. These two procedures, although they look very much not alike, it turns out that they're inverse, the one to the other, in the following sense. That if under this correspondence you associate to X a certain pair of tableaus, then X inverse has just the same pair in reverse order. Now, the Kazhdan-Lusztig result that I was referring to before is the left cells are described in terms of the Robinson-Shinstead correspondence. Actually, the left cells are described like this. So Kazhdan and Lusztig proved that two elements, okay, X and Y are in the symmetric group on n letters. Two elements are in the same left cell if and only if the Q tableaus are equal. So that's a very nice combinatorial description of the object. Now also, it was worth seeing this because this will maybe give a hint of also what McDonough and Palikaros did in the thing on Specht modules. So for this, let me just briefly explain what these Specht modules are. Well, they are it's a family of modules for H, where H here is really the Hecke algebra of the symmetry group on n letters. They are labeled by partitions of lambda, by lambda partitions of n. And such an S lambda is free over A with some standard basis, which is indexed by the set of standard lambda tableaus. So lambda is a partition, and you look at all standard tableaus of that shape, and this is how you label the basis, the standard basis of the Specht module. And such a Specht module comes equipped with a symmetric bilinear form, which is also H equivariant. And, well, under specialization, you get some specialized bilinear form there. And you can think of the radical, which is a submodule, actually, of S lambda k. And then, what Dipper and James showed was the following, that if you look at if you quotient out the radical of that symmetric bilinear form, and you look at those d lambda k's, so you are in any specialization, it turns out that these are exactly the irreducible representations of HK. That's quite a strong result, because you have a nice uniform description for all irreducibles of HK. Of course, there is something to be said there. These are the irreducibles whenever this radical is not, how should I say, whenever d lambda k is not 0. So this happens when d lambda k is not 0, actually. So then the question is, when does this happen? When does this symmetric bilinear form, when is it non-zero? Well, it turns out that the answer is, of course, it depends, it has to depend on the specialization, of course. And how? Well, you define E to be, well, it's basically the order of theta of V. V was the parameter, theta of V squared as a root of unity. So this is E. Now, if E is bigger than N, then beta lambda k is always non-zero, so the reducibles are just, it's even stronger than that, are just the Specht modules. This case includes also the capital K. And they even showed more than that. They gave a nice combinatorial criterion for when this happens, for when this is non-zero, and this happens if and only if lambda is irregular. So lambda is a partition. It is irregular if it has no more than E parts. So out of all its parts, it never has more than E equal parts. So this is the situation in type A. I should probably say that, of course, by what we have seen before on cells, this also gives you something on the right cells, X and Y, and in the same right cell, if and only if the first tableau of X equals the first tableau of Y, and they're in the same two-sided cell, if and only if, well, the corresponding tableaus have the same shape. Which means basically that cells are described by tableaus, really by standard tableaus, whereas two-sided cells are described by partitions, by shapes, simply. Okay, another example in type B. Well, in type B, there we have two conjugacy classes of parameters, so there's a possibility of giving them unequal values there. So let's call the parameter associated to the first generator, the parameter, let's call it capital V, and the parameter for the others, which are all conjugates, small v. So gamma should be some group which contains at least this. So all monomials in capital V and small v. So then A will be this ring. And now let's stick to exactly this choice. So I'm making here one choice of an order relation. And that choice is, if you look a bit at it, it's actually lexicographic. So lexicographic with V, with capital V really dominating completely the small v. This is the idea. We have called it asymptotic case for, well, for some reason. It gives some asymptotic behavior of the algebra, but this is possibly because we didn't find a better word. In any case, so this is the order relation. Remember, in order to have a Kazhdan-Lusztig theory, you have to decide something about that. So this is what we decided there. This is one case that we studied. And it turns out that this is the one case which is very similar to type A. So we are in type B, but this thing has a very similar behavior to type A. So one thing with similar behavior is that the left cells are described in terms of a signed Robinson-Shenstedt correspondence. So, and I will not give another example again, but I'm just going to say the following. What is that signed Robinson-Shenstedt correspondence? Well, you can realize the Coxeter group of type B as a subgroup of the symmetric group on two letters. So what you get, I will not make this story very long, you can describe a permutation as, not a permutation, sorry, an element of Bn as some signed permutation. So let me give here an example. I'm just taking a variation of that, but putting some signs there. Well, what I mean really is that it's permutation on 2n letters, so here you should have -1, -2, -3, and so on up to -6. And if 1 goes to 2, then -1 goes to -2, and so on. So 3, the image of 3 is -3, so the image of -3 is 3, and so on. So it's enough to know half of it. So with this, so it's enough to work with this half. And when we say this signed Robinson-Shenstedt correspondence, what we did is, I mean, this was something which was known. The Robinson-Shenstedt correspondence will be between the Coxeter group of type B and the set of all pairs of standard bitableaus. Of total size n and with a filling with numbers from 1 to n. So what you get here is P1, P2, and Q1, Q2. 2 tableaus here, 2 tableaus here. And what are these 2 tableaus? Well, the first, I mean, it's easy to I will not do it now, but it's easy to explain. The first tableau is the tableau obtaining by insertion, the same insertion procedure, but performed only on positive entries here. Whereas the second is you perform it on negative entries. And these Q1 and Q2, as before, they just keep track of what you did. So what you get is really pairs of standard bitableaus of the same shape, total size n, and so on. And the result is really very, very similar. Namely, X is in the same left cell as Y. Let me call this Q underlined and P underlined. If and only if Q underlined X equals Q underlined Y. So it's really the same result as in type A. You just look at the Q tableau here, they just look at the Q tableaus. There are two of them, but that's all. So this is the asymptotic case, very similar to symmetry group. And it is, I mean, the similarities continue, really. Of course, I wanted to say Q of capital V and small v, the field of fractions of A. If you look at that, then all the cell representations are irreducible, and all the irreducibles arise in this way. And the analogy continues. There is a theory of Specht modules which was developed by Dipper James Murphy in '95, and they really introduced such a family of modules labeled by bipartitions of n, and showed that if you look at this specialization exactly where k is the field of fractions of A, then those modules, I mean, the specializations of those modules are exactly the irreducibles. And again, you can ask the same question: is there a connection between those Specht modules there and those cell modules? And again, the answer is affirmative, so the analogy really keeps going. There is a canonical isomorphism between those Specht modules and the cell modules. And I will not go into much detail there. The only point I should have made actually before is that this I'm saying this construction does not depend on the choice. So please note that, okay, in the case of equal parameters, so in type A, you don't have an order because parameters are equal. But here, where we did make a choice of an order. We did go through the Kazhdan-Lusztig theory. Dipper James Murphy, no, they didn't. They just look at the Hecke algebra where there's no order relation on the parameters. There's no Kazhdan-Lusztig theory there, nothing. It's just the amorphous, if you like, Hecke algebra, and they produced these Specht modules. So it turns out that there is this nice canonical isomorphism between these Specht modules and exactly those cell modules obtained by the asymptotic choice. So they constructed the Specht modules labeled by bipartitions of n. They have the same formal properties as in type A, namely they are free over A with standard basis indexed by standard lambda by tableaus. If you specialize, if you extend scalars by some specialization to the field of fractions of A, then the irreducibles are exactly this specialized Specht modules. And under any other specialization, we get a nice collection of, a nice description of the irreducibles of that specialized Hecke algebra, exactly as before. What is more complicated here is the aspect of, before, if you remember, in type A, this B lambda k was non-zero if and only if lambda, the partition lambda, was irregular. Here, the irregular is the analogous of this irregular thing is much more complicated than just what you would be tempted to think at a first approach, that possibly just the two parts of the bipartition. No, more than that. But so they formulated the conjecture back then in '95, and this was proved last year by Iancu and Jacon. So this is a very nice and round picture. What is left? Well, this was only one example of only one setting. This was this asymptotic case, a certain precise choice of an order. It's actually quite a big, it turns out that it's quite a big chunk of possible choices, but still there are many others out there. So what are the remaining cases in type B? Well, setting is the similar and the same. I mean, parameter corresponding to the first generator denoted by capital V, the other by small v. This would be gamma. This would be A. Well, I have to make choices. So this is the aim. I mean, what is left to be done to determine the left cells of W for all possible choices. And what do we understand by determine the cells? Well, something like that. Some nice combinatorial thing. Nice combinatorial description. And then, once you do this, ideally, you should be able to decompose at least this one, where capital K is the field of fractions of A. So the cell representations into irreducible. And in particular, find out when these are themselves irreducible. Is there a Specht module theory then? So we're doing now come the answers, but the answers come in the form of conjectures. And here are the descriptions that we found. But we have not yet proved everything. I will say immediately what is missing there. So for the time being, suppose that gamma plus is like this. So saying what is positive means say something about the relative position of capital V and small v. So if V is between two consecutive powers of small v, positive, well, non-negative consecutive powers, then, first of all, the partition only depends on R. Well, I mean, there is a point there to be made, and it only depends on R. It doesn't really, it's not, as soon as it's between V to the R and V to the power R plus 1, the partition into cells depends only on R. It's not important if you are closer to V to the R or closer to V to the R plus 1 or whatever, or in the midpoint exactly. The cells are explicitly described, and in the same sense, explicitly described by a generalized Robinson-Schoenstatt correspondence, but this time it's more not so user-friendly. It involves domino insertion into a 2-core, and that 2-core actually has size R. This is where the R comes into play. And then, in such a case, the cell representations of H sub K, sub capital K, are irreducible, and all irreducibles arise in this way. So this is would be a very nice result. For the time being, it's conjecture. And then what is left in terms of possible order relations is such a situation where V is equal to some power of, capital V is equal to some power of small v. And in that case, it turns out that, it should turn out that the cells, be them left, right, or two-sided, are the small subsets of W, which are the same times unions of cells obtained from the R before and from the R after. So you have V to the R, V to the R plus 1, and V to the R minus 1. This is a small v. And if capital V equals this, then the cells for this choice of parameters are obtained. I mean, that's the smallest subsets, which are at the same time unions of cells that would be obtained when you would have V between V to the power R minus 1 and V to the power R, which are described in the preceding conjecture, and here, again, described before. So in some sense, as soon as we get a hold on the first conjecture, well, there is some theoretic result there, but there is no more combinatorics, no big combinatorial machinery to develop, because this is what we say. Once we know what happens between, then we also know what happens at those points. What is the evidence? Well, first of all, at least we checked it for some small values. And more seriously, we could reformulate it and they were actually formulated at the beginning in some other way, which, in a natural way, which included what we did in the asymptotic case with Cédric Bonafé. So that's actually evidence for these two conjectures. It just says that I should say it's something like this: the conjectures hold for r greater than n minus 1. It's hidden there, but this is what we did. The asymptotic case corresponds to both of these conjectures for r greater than n minus 1. So that's also some evidence. And even more serious evidence, Cédric Bonafé recently proved one half of the conjectures. That is, he showed that if two elements are in the same combinatorial cell, so if two elements have the same Q tableaus, say, then they are in the same Kazhdan-Lusztig cell. So what is left is only one implication. And he was based on the work of Pietraho and Tuskin on domino insertion. Since I'm talking about Pietraho, and I will quickly finish here. Since I'm talking about Pietraho, I just want to say that very appropriately he has put a paper today on arXiv, which gives some meta-evidence, not proper evidence, but meta-evidence in the sense that he shows that if Lustig's conjectures, there are 15 conjectures about the behavior of Hecke algebras with unequal parameters. If those conjectures are true, then our conjectures are true, something like this. So this is what he proved very recently. And what we have, it should be actually 2007, what we have there when we stated our big conjectures there is that the statements hold for r equals 0 and r equals 1. And moreover, they are consistent with behavior similar behavior in dihedral groups and F4. And the last conjecture is that in that case where V is between two consecutive powers of small v, then the Kazhdan-Lusztig basis is, so there where nice things happen, the cell representations are reducible and so on, then the Kazhdan-Lusztig basis is a cellular basis in the sense of Graham and Lehrer. And what does this mean really? It means that it comes with a Specht module theory. I mean, I had to answer this question as well. It really means that we can make a collection of left cell representations, and those will be actually, so a selection maybe. That selection will be exactly the set of reducibles. We can put bilinear forms on those with exactly similar properties to formal properties to what we have seen before for Specht modules. The reducibles of any specialized Hecke algebra will be given by such quotients of the cell representations by the radicals of the bilinear forms. And there's some evidence because, again, in the asymptotic case, this is done in various papers, in various combinations of these three people, Bonafé, Geck, and myself. Then the existence of the cellular structure at all can be deduced from Lustig's conjectures, and this is what Geck showed in 2007. And such a, because you need here to know how to make the selection there, so this lambda, and not only this lambda, sorry, this lambda R0, which is some sort of generalization of irregular to other choice, to Bn and to other choices, are determined by Geck and Jacon. So basically what it says is that for each R, so for each such order and each R, there is a different theory of Specht modules. So I know I should give a proof, says the says the folklore here, but the only non-technical proof which I can find is this one. So I will stop here. Thank you.
Any questions?
Why are they called cell? Why the word cell?
Sorry?
Why is it called cell?
Oh, there is some connection with geometry, and yes, there is. I mean, you can think of, at least if you look at type A, you can really think of this in terms of some geometry. And not only that, actually, if you start with this G, and which is some, and the Borel there, then you can think of well, start with G as GLN, okay, and think of the Borel. And then if you look at this G over B, for instance, where everything starts, really, I mean, this, if you remember, this G over B was the starting point to arrive at the Hecke algebra. You can think of this as some flag variety and so on. So there's a geometry in the back of this story. So this, I think Kazhdan-Lusztig originally were motivated by questions about primitive ideals and such. Primitive ideals and such. So it has a connection to geometry. I cannot now say exactly this really corresponds to such a specific cell. So it's more, I think it has a geometric flavor. So this is what motivates.
So you had this asymptotic case where capital V is bigger than all powers of small v.
Yeah.
So is there something like an anti-asymptotic, or is there a case where small v is bigger than all powers of capital V? Is that?
Yeah, but it's not. I mean, well, yeah. Well, short answer is yes. There is a case, of course, and that would correspond simply to the situation where capital V is between.
Oh, okay.
Yeah. So it's really at the other end of the spectrum, but and yeah, in some sense.
Oh, so and that's one of the cases where you already proved conjecture one.
Well, half of it.
Oh, half of it. Okay.
Yes. Yeah. For some reason, it is not as similar to type A as it's the other one. So the asymptotic is really the one which has the maximum of similarities with type A. Whereas, so in some sense, it looks like that would be the a natural choice for parameter, or if you want, it's almost as if you didn't have unequal parameters. I mean, it's nicer than the selection of equal parameters actually on type B. This is really strange about that.
And then in the asymptotic case, for this combinatorics, is it easy to say what the two-sided cells are?
Oh, again, it's the same thing, same shape.
So there's one two-sided cell for every representation? So then you get the two-sided cells are represented by bipartitions.
Right.
Okay.
So in reducible representations,
okay.
Yeah, you will see them in the two-sided
Okay,
cells.
so
True. Yeah,
I see.
exactly.
Any other questions? Okay, well, let's thank the speaker again.